A ship feels its way through fog, bell sounding the seconds, while below decks a clock refuses to drift. The sky won't give a star, the coast hides its shape, and yet the captain can still draw a thin, confident line on the chart. This case asks a sharp question. How did 18th century sailors learn to know where they were east-west when the world looked the same in every direction? The core idea is simple. They solved longitude by carrying a stable reference for time and comparing it to the sky. Because the sea never sits still, the answer depended on a clock that stayed honest through motion, salt, and months of weather. Longitude is your position east or west on the globe, measured in degrees from a chosen meridian. If you know the time at that meridian and the time where you are, the difference tells you how far around the world you've sailed. The Earth turns 360 degrees in 24 hours, therefore 15 degrees per hour, so 4 minutes of time error equals 1 degree of longitude, roughly 60 nautical miles at the equator. First, why time matters at sea. Local noon, the moment the sun stands highest, gives you your ship's local time. If your onboard clock shows the time back at the reference meridian, the gap between those two times turns directly into east-west distance. Here's the cause and effect in plain words. If the clock runs fast, it tells you the home meridian sun has already passed noon, meaning you are to the west. If it runs slow, you are to the east. Which meant the ocean problem was not mathematics. It was building a clock that kept the same beat day after day, despite cold, heat, shocks, and the long, slow heave of a rolling hull. In 1714, after costly wrecks and guesswork, the British Parliament offered prizes for a practical solution. The largest reward would go to any method that could find longitude within half a degree, about 30 nautical miles, after a transoceanic voyage. This date anchors the new era. The Board of Longitude turned a riddle into a public engineering challenge. Two paths emerged and finally worked together. One path was the lunar distance method. Measure the angle between the moon and a known star, compare it to tables that predict the moon's position by Greenwich time, and compute the reference time from the sky itself. The other path was the marine chronometer. Carry Greenwich time with you in a box and protect it from the sea's mischief. Because each path had limits, captains liked having both. The lunar method needed clear skies, careful angles, and almanacs. The chronometer needed craftsmanship and money. Therefore navigators cross-checked, sextant to the sky when it cleared, chronometer ticking steadily when clouds blocked the heavens. The chronometer's breakthrough was reliability, not magic. John Harrison, a carpenter with a mechanic's patience, built clocks that corrected for temperature, friction, and shock. Bimetallic strips bent predictably as brass and steel expanded at different rates. Jeweled bearings minimized wear. A remontoire gave the balance a steady push, no matter how strongly the mainspring pulled. Because the ocean is a harsh lab, trials mattered as much as theory. In the early 1760s, a compact sea watch, later nicknamed H4, sailed the Atlantic and returned with errors so small that navigators could trust its beat over weeks. Meanwhile, tables printed in the Nautical Almanac from 1767 made lunar distances faster to use, turning night skies into portable clocks for ships without an expensive chronometer. Next came adoption by practice. James Cook carried K1, a faithful copy of Harrison's design, and tested it across immense southern routes. His journals show a quiet revolution. Day after day, he took local noon, compared it to the watch, and wrote down longitudes that matched landfalls instead of arguing with them. Fog, the old enemy of seamanship, lost part of its bite. A ship could dead reckon through a grey week, tallying course and speed, and then, when a small blue patch opened for the sun, pin local noon and check the chronometer. If clouds stayed all day, the watch still marched on. The first clear noon gave a position that kept the next leg honest. Accuracy lived in minutes and miles, not absolutes. A chronometer that kept time to within 1 minute over an ocean crossing placed a ship within about 15 nautical miles at the equator, often the difference between a safe channel and a shoal. And because each minute mattered, captains began to carry 2, 3, even 4 chronometers, averaging them, and retiring any that drifted in suspicious ways. There was a boundary condition to remember. Chronometers were costly and needed care. For decades, many merchantmen relied mostly on lunar distances, resorting to chronometers as prices fell and copies multiplied. By the early 19th century, competition among makers like Arnold and Earnshaw made the trusty box chronometer a standard fitting, not a royal luxury. Daily shipboard life changed in dozens of small motions. The noon sight became a ritual. Quartermasters brought up the sextant, the officer of the watch called out the sun's dip, and the log slate recorded local time to the half-minute. Below, the navigator compared it to the chronometer bolted in its gimbaled case, corrected for equation of time and instrument errors, then walked a fresh longitude to the captain. Charts improved because positions improved. Surveyors could fix reefs and capes to repeatable longitudes, so the next chart edition moved hazards into the right water. Insurance rates responded. Convoy timetables tightened. Harbour pilots knew when to look to the horizon for sails that ought to appear. Exploration shifted from heroic estimate to planned experiment. On Cook's tracks, measured longitudes let cartographers stitch coastlines with fewer gaps. On merchant routes, predictable landfalls shortened voyages and saved fresh water. Which meant that timekeeping wasn't just a sailor's trick, it was a state capacity that paid back in freight, tax, and safety. The new precision also changed diplomacy and law. Treaties that defined borders by meridians gained teeth when surveyors could actually stand on the line and mark it. Naval orders grew more specific. Rendezvous at a set longitude on a set date, not at the usual ground, where currents and guesswork used to scatter fleets. Uncertainties should be acknowledged and set aside. No single inventor carried the whole victory. Clockmakers refined balances, escapements and cases in competitive bursts, while astronomers ground the moon's motion into numbers that sailors could trust. What matters is the convergence, a seagoing clock stable in weather, and tables that turned the sky into a verification tool. Because measurement encourages more measurement, the chronometer seeded new habits. Officers kept rate books for each watch, tracking how many seconds it gained or lost per day, and adjusting positions accordingly. Port time balls dropped at advertised hours, so ships could reset on arrival, knitting harbours into the same invisible time grid. Even disaster prevention acquired a clock. Sailing directions began to warn, "Do not make the landfall east of XD Ground," turning former guesswork into guardrails. Fairway buoys and lights were charted by precise coordinates that matched what a chronometer would tell a cautious captain at night. Margins grew thicker where they needed to be, and thinner where time saved money. A single example brings the method down to fingertips. At local noon, your sextant says the sun peaks and your chronometer reads 14 scarce at Greenwich. Greenwich is 2 hours ahead of your local time, therefore you are 30 degrees west of Greenwich, an answer you can plot in a heartbeat while the helmsman keeps the ship's head steady. By the century's end, nearly every navy required chronometers on long voyages, and major ports synchronized public clocks to a standard meridian. The habit of knowing where you were exactly made oceans feel smaller without moving a single shore. And like all good tools, the chronometer faded into the background of ordinary competence. Finally returned to that ship in fog with a clock that refuses to drift. The sea still hides its edges, the wind still changes its mind, but the line of time holds steady under the navigator's hand. From that line, longitude unfolds, and with it routes, schedules, charts, and the quiet confidence to meet land where the chart says it will be. The takeaway is crisp. Once you can measure time reliably, you can measure empire, because accurate minutes become safe miles, and safe miles become power. If this open case file brought the ocean's clockwork to life, like and subscribe for the next episode.